So let's now talk about what is really the heart of the matter here. How do we develop the conditional distribution over distance, given that you have this marginal distribution over direction? Let's turn right now to that. Now, one way to think about that is to actually look at the shot dispersion patterns that I showed. But as I mentioned, let's just assume for the moment that you've hit a shot that's exactly on target. It's going straight at the target. What's the probability distribution now over how far long or short it might be? Well, what I mentioned before is that significantly short is more likely than significantly long. So I've put in here 80% chance that you'll go within this range from 3 yards short, from 5 yards short to 3 yards long, 10% chance of being longer than 3 yards long, and 10% chance of being shorter than 5 yards short. Again, that's pretty reasonable. This tends to have a narrower range in terms of yards than the direction. And so, yeah, I think, this is a pretty good place to start. Now, what about, however, suppose you had the information that the shot is actually 10 yards right. Well, that would cause me as a golfer to believe that my probability distribution is now, the whole thing is moved more toward the shorter side. So what you can see that I've done here is I've simply subtracted 2 yards, and I've got the same 1090 range here, but the whole distribution has shifted a couple of yards because given the information that my first shot is 10 yards short. You would do the same thing, something similar, if the first shot is 10 yards left. And basically what I've given now is a rule for conditioning the quantile parameters of distance based on the outcome of direction. And that rule is simply, as stated here, the median distance increases by 2 yards for each 10 yards of direction left. The 1090 range differences remain constant. If you go through those equations that I just showed, it leads to a very simple Metalog equation for this probability distribution, which now depends on x1, the result of direction. If you have, and that's the important characteristic of it. You need to know the result of direction in order to have your probability distribution over distance. And you can see here the corresponding curves to this equation, which have exactly characteristics that I just mentioned. If you hit the ball left, it tends to be farther and so forth. So let's now let's talk about what we've just done. What we have just done is we have effectively parameterized this entire shot dispersion pattern with 9 points off of this tree. And you can see the 9 points that are right there. This means that parameterizing a multivariate QPD is as easy as doing a conditional probability tree of the kind we would use in decision analysis all the time. And it's really just these 9 points with the relationship that I've put that connects them for in-between points that parameterizes the whole shot pattern. Critically and importantly, these control points, these assessed points, or points that are determined from data, can be moved around in any way you want. You could take this point, move it up here, take this and move it down here. You could take these and move them closer together. Actually, any rule whatsoever, it doesn't have to be linear as I just showed, any rule whatsoever can be used to condition the parameters of distance as a function of direction. Once you have this, it's very easy to simulate. If you just pick a random sample from a uniform distribution, which is a Y1, you plug it into this equation, you get your sample for direction. If you pick if you pick a random sample from a uniform distribution, plug it into this equation. And by the way, I don't know if I said on the previous graph, yeah, this is the equation that results from this simple rule assumption. And so you just plug Y2 into this equation, you get your simulated value, and that's what gives you this entire shot pattern. The nice thing about this is you can parameterize the shot pattern to be tailored to whatever happens to be your specific golf game or your specific peer group. The resulting joint probability distribution can be plotted in 2 dimensions. It's like a 2-dimensional bell-shaped curve, which has all the desirable characteristics we just mentioned. Also, any multivariate probability distribution has implied distributions that typically do not have an explicit functional form. Well, with the metalogs, those can be fairly easy to get. For example, we have the marginal distribution over distance, but we don't have, over direction, but we don't have the marginal distribution over distance. But to get that, we can just line up all the results, the yellow dots, from the simulation over distance and direction. And here I've just lined up the distance dots, and we can easily fit a 3-term metalog to that. And you can see it's a very accurate fit. However, if it weren't a very accurate fit, in another case, you could use a 4-term or a 5-term metalog. With adding terms, you'd certainly get enough flexibility to capture most anything. This corresponds to the curve that has the skew short capabilities or situation that we mentioned.